We will go over example 2.2 in the textbook on page 15. This is going to be our first example where we actually solve a differential equation. This is not technically a partial differential equation, as there's only one independent variable in this problem, but it is going to give us experience with solving a problem with boundary conditions, which is a crucial part of solving partial differential equations, and something that you may not have seen in your ordinary differential equations course. So, the physical situation we're going to consider is the case where we have an aluminum bar 1 meter in length where the ends of the bar are going to be fixed at 20 degrees and 30 degrees respectively. In order to keep the units all consistent, we convert our x variable into centimeters rather than meters. So the x variable is going to run from 0 to 100. Now, mathematically, the way we're going to simplify this problem is we're going to eliminate the time variable from the heat equation by considering what is the temperature distribution of this bar after a sufficiently long time so that the temperature is no longer changing. This is what's called the steady state temperature distribution. So we are considering what the temperature distribution of the bar is after the temperature has sort of settled down. And this is modeled by the following differential equation. We have negative 1.5 times the second derivative of u. U is, again, the temperature distribution, is equal to 0. And for our boundary conditions, we set the value of u at 0 equal to 20, and the value of u at 100 equal to 30. We begin with the differential equation. The first thing we're going to do is divide by negative 1.5. Since it's 0 on the right-hand side, we can do that, and the 1.5 simply disappears. We then integrate both sides, integrate once, and we see that the second derivative turns into a first derivative, and we must remember our constants of integration. Remember when your calculus teacher said, remember your c's? This is why. The plus c's are absolutely crucial in order to solve differential equations. So by integrating the right-hand side, the integral of 0 will be a constant, and we're going to call that constant c1. In order to solve for u, we integrate one more time. Now the derivative disappears, and we get that u of x is equal to c1x plus c2. Now our goal is to find those constants of integration using the boundary conditions. Using the first boundary condition, we have that u evaluated at 0 is equal to 20. Plugging this into our equation, we see this is simply going to give us that c2 is equal to 20, because u evaluated at 0 is, in fact, c2. Using the next boundary condition, u at 100 is equal to 30, this gives us the equation 100 times c1 plus 20 is equal to 30. Now, this is a simple linear equation that we can solve for c1, and it tells us that c1 is equal to 1/10. So therefore, our final solution will be 20 plus x over 10. All right, the temperature distribution on this bar is going to be a linear equation with slope 1/10. So we see how these boundary value problems can be solved in a very similar way to the simple problems you saw in your ODEs class, using the boundary conditions instead of the initial conditions to determine the constants of integration that appear as you integrate through your problem to eliminate the derivatives.